Okay, so hello everyone. My name is Pavlo Gavrylenko, and I will teach you equations of mathematical physics, or it is also called advanced mathematical physics A. First of all, if you want to ask something, just write to my email, this one. And also, if something is unclear during the lecture, just interrupt me and ask. So everything can be adjusted so that everyone understands what's going on. I will also ask you to write your emails so that I can use and I can send you the literature, some updates, some problems, etc. Please.
Our university email or personal?
It doesn't matter. The only important thing that it is actually working. Because I remember that sometimes university emails did not work, and I don't know why. Mm. So, emails and names. So uh, you also start learning more what your name is, but maybe not immediately. And also, please ask those who are not present to write to me so that I have contacts of everyone. And also another remark is that tomorrow's lecture is in the room 004. Probably it will be different on the next week, but I don't remember the other room number. Okay, so let us start from some introduction. So those are some equations on. So maybe I will just write several examples. Those are equations on one or on several functions of several variables. For example, equations like this. So it can be equal either to 0 or to some source, some function. And the problem is always to find this function u. Also, these equations can have some boundary conditions. Like we can have conditions on the following type. That this is a coordinate plane with coordinate x and y, and there is some rectangle, for example, and this function u of xy equals to 0 on this on the boundary of this rectangle. Maybe we can call this d, and this will be boundary of d. So u of xy is equal to 0 on boundary of d. So this is what is called Poisson equation, or if it is there, it's called Laplace equation. In 2 dimensions, 2D. Also, I will use some shorthand notation for this partial derivatives. These notations are the following. So, d2 u dx squared is dx squared u is uxx. Also, people write it as dxx. So those are all equivalent notations. So, so equations like this, possible plus some other second derivatives equal to 0 is called Laplace equation. Well, it's example 1.1. So another example of this kind, actually, I will not erase some of these formulas because they will be useful in one of the examples. So was it the first lecture on some geometry course, or was it something different? Ah, okay. So maybe I'll write it like this. So there is a Laplace equation in 2D, and there can be in principle the same equation in arbitrary dimension. This is 3D Laplace equation. So another example is a so-called wave equation. The only difference is that is the sign in this differential operator. And this is called 1 plus 2 or 2 plus 1, it doesn't matter. So, and we will find why it is called wave equation. We'll derive it today in several examples. So another equation is almost like this, but with the first derivative. This is called. Does anyone know how this equation is called? Hmm? Yes, it's one of the possible names, examples where it appears. So, yes. Common name is the heat equation, but of course it also describes diffusion. Basically, did you see it in some courses, or you just know what it is? So, have you ever studied any of these equations in some of the courses? Mm. Ah. Mm. and to what extent, how to derive them or how to solve them.
Solve them in an electromagnetism, like the cellular plot.
Ah, mm-hmm. But it's not for everyone, right? Or ah, okay, so uh, then I'll probably not assume that everyone knows everything. Because, yes, so there is this equation. There is uh, um, so there are most common equations which we'll study, but there are also slightly more complicated examples which also appear in nature. For example, uh, this equation. Mm, minus- It's called 2D Helmholtz equation. Uh, and there is so it appears so it can appear from any of these equations when we consider specific problems for them, but it can also describe some phenomena like straining in plasma or some other problems of this kind with some exponential suppression. And the last example, which appears in quantum field theory, and I actually don't know other applications of it, is called Klein-Gordon equation. So it is 2 plus 1 Klein-Gordon. So today I'm just writing these equations as some practical examples of what people are interested in. But tomorrow, or maybe also today, I will show that all these equations naturally appear as a result of classification of such kind of second-order equations with constant coefficients. So it's not just a list of random formulas. Okay. So far there are no questions, right? Okay. So let us try to see how some of these equations can appear in some problems, and also what other objects can appear. Um, so okay, so the first one will be Laplace equation, or maybe Laplace plus one. So of course it can appear in electrostatical problems, but it can also appear in a slightly different setting when we study electric circuits. Namely, if you decide to study current in some conductor. Uh, so. So let us consider this problem, and let us actually try to discretize this problem. It can appear either if you study this specific electrical circuit, or if you just choose some model to describe some continuous medium. So let us consider this resistor network. So, so I will not draw all of them, but all of them have the same resistance. So, so what we have here, we have a grid with vertices labeled by two integer numbers. So this is xy, this is so this is x and this is y. So this point is x, y plus 1. This is x plus 1, y. And what we have in this network? We have some potentials defined in these points. So we have some and we have some currents that goes through this resistor. So and this currents go between two neighboring points. So maybe the best way to denote them is to introduce some already defined notation. I x of is ix of 2 points. A current that goes from point xy to point x plus 1y. And there is also current in y direction. So, and if you want to describe distribution of potentials and of currents in this problem, we need to write two things. One is Ohm's law that relates differences of these potentials to currents. So we know that 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 difference of potentials equals to I times R. And in our particular situation, it means that mm, this current mm, will equal to 1 over R times the difference of potentials. Maybe I'm missing the sign. So actually need to write which current is written in what point. So this one will be so it will be difference in opposite direction like this. And the same formula for another current. So there are this Ohm and there is Ohm's law. So there's first thing to write. The second thing to write is that we have a current conservation in each of these points. So let us look at this picture. Mm. And let us actually say that there is also some possible inflow of electric current in this point, which we denote G of xy. So let us add it here. So let us write this current conservation. So we have this external current that flows into point xy. And it equals to currents flowing from this point. So it equals to Ix of xy x plus 1y plus and once it is written, we can combine Ohm's law and this current conservation and write a single equation. Actually, these two laws together are called Kirchhoff's law, and they are sufficient to compute any current and potential distribution in any circuit. So, combining this, we get the following equation. Maybe I need more space. So something like this, and it can be further arranged. Uh, there is one way to write it, and another way to write is just to combine all these files together. Yeah, why I wrote this formula? Because here we see such thing as discrete discrete approximations for second derivatives. So
Can you simplify delta the width of the grid?
Hmm? Yes, but in principle, we can just say that these functions are smooth enough so that shift by one is fine in the Taylor expansion. So, because this size of grid is just some counting parameter. Uh, It when we send a size of grid to zero, it means that we are dealing with some function that is smooth enough, and so that when we take a small enough grid, then this function will almost coincide at neighboring points. We can just say that we have such a function from the very beginning. So, uh, so let us look at this. Uh, this is variant A, and this is variant B. Mm. By smooth enough, I mean that it varies very slowly. Maybe better to write it in that way. So then we can expand it as a Taylor series. F of x plus 1 y equals to phi of x y plus phi of plus phi of phi x of x y plus 1/2 phi xx of x y plus and so on. Now let me check the column. So and then when we consider a combination like this, if you consider a difference of uh, yeah, we can also say that the second derivative is much smaller than first derivative, much smaller than the function itself. So, so it happens in a situation when we have some 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 function that changes very slowly, and we take uh, take a difference of its values at two neighboring points. And this is x, and this is x plus 1. So when we have this, we can consider first differences. Mm. And the second derivative. So if we look at this formula, then we see that this first derivative term and this constant term will cancel, and we are left with just the second derivative term. So this is phi xx of xy plus some corrections. So if you take all these calculations together, then we can see that this equation in the continuous limit can be written as j of xy equals to minus phi xx xy minus phi yy of xy. Oh, sorry, of xy. Plus some correction that can be neglected. So this is the Poisson equation. But we'll also look at the discretized version because in some sense it might be useful for some intuition because it shares most of the properties of differential equations, but does not have various infinite dimensional or functional analysis things. So. And I wrote this variant B because this equation can be generalized to arbitrary graph. There is such thing as a Laplace operator on a graph. So this can be written as 1 over r minus 1 over r sum over neighboring points. How to add this? Let us use big letter, maybe x prime, or maybe let us write it like this. So there is sum over all neighbors of x of point xy, and the summand is phi of x prime y prime minus phi of xy. This is called Laplace operator on a graph. Laplace on a graph. And also one more notation which we'll use is a notation for Laplace operator itself. So or if it is a higher dimension, it will be it will have more terms. Plus possibly something else. Yeah.
So does this material like
understand the
Maybe
equation.
like next semester will we do like Einstein's equation?
Mm, on instance, do you mean gravity or which Einstein's equation?
Oh, I was just thinking about when you put the Laplace operator on the curved
Ah, uh, yes. Let me think. Is if it is realizable in this mm, mm, in this electric setting. So we can definitely put some different uh, resistances here, but I'm not sure that we can mimic arbitrary metric in this way. So in 2D maybe it's true. Mm, so or maybe if we allow some additional resistors go in different directions, and then we can realize anything. Mm, and maybe we also need to perform some redefinition to multiply something by a square root of determinant of metric. So I think it should be doable. Yes. Next question. Hmm. Okay, now let us look at different equations that can be obtained in the same way. So uh, maybe I can also, or there is a sort of equation. Mm, so- And we can work in the same setting. So we have the same grid. Mm. But now this points of a grid correspond to some objects with a given heat capacity. Mm. Let us call it by C. And these lengths of a grid correspond to contacts between these objects. And since temperatures of these objects are different, there are some heat flows between them. Mm. Mm. Let us with heat capacity C, and sorry, I forgot to write, and with temperature T, T of xy. So here we have heat flows Qx and Qy. Maybe heat flows or heat currents. Maybe currents. So the situation here is almost the same because we have conservation of the heat current and we have an equation that defines it, and namely a heat current is proportional to a difference of temperatures. So we have a formula that Q equals to some coefficient times delta T. So the analog of Ohm's law. So it can be compared with I equals to 1 over R U. And second equation is that sum of currents, sum of Qx, well, I will not write points explicitly, but this sum Qx plus Qx plus Qy plus Qy will now correspond not to some external flow, although we can still add it, but it will correspond to the flow going from this object. And since this flow has some energy, it will cause a decrease or increase of temperature. So this sum of flows will equal to this heat capacity with sign minus if you follow the computation carefully. So it will be heat capacity times time derivative of temperature. So if you combine this together, then we get so maybe I will write a Laplace operator without specifying precisely whether it is on a lattice or it is a continuous Laplace operator. So you will get this equation: dt over t equals to kappa over c Laplacian of t. And so, and in principle, we can also add some external flow here, plus 1 over c q external. So there is a heat equation. And you can also notice that it was derived in a very similar way, and actually it can be used to get this Laplace or Poisson equation if we specialize to to special kind of problem with time-independent temperature distribution. So if we have some external currents and we wait for some time, then this temperature distribution stabilizes and mm, uh, and mm, this equation becomes precisely the Poisson equation. And this is a typical situation that if we study some more complicated equation, specialized to some stationary problem or a problem with some specified time dependency, it can be reduced to some other equation from this list, like here. The heat equation can lead to Laplace equation.
Do you ever use that fact to like perturb away from one solution to a new problem? If you know, like for a stationary problem, you know the solution and you can study it maybe perturbatively.
What do you mean by perturbatively?
I'm just adding some small source and seeing how the solution changes.
But here it doesn't matter whether this source is small or not, because these equations are linear, and so solving a problem for small source and for a big source for big source is the same. So maybe it's an important thing to notice. Yeah, probably I can also already erase this list. Mm. Remark that all equations are linear. And consequence of this is that sum of solutions is also a solution. Maybe I can write it like this. So, for example, we can have some solution of the heat equation like dt T1 equals to Laplacian of T1 plus Q1, and dt T2 equals Laplacian of T2 plus Q2. Then if you take sum of these two solutions, then dt of T1 plus T2 equals Laplacian of T1 plus T2 plus Q1 plus Q2. Actually, such things which appear as inhomogeneities on the right-hand side are called sources for equations. So these things are called sources. So this is one phenomenon that if you have two solutions with two different sources, we can take their sum and get a solution of equation with sum of sources on the right hand side. And another phenomenon is very similar. It says that if you add, if you take a homogeneous equation, then you can add any solution to the homogeneous equation. And add to it, and it will be again a solution of the same inhomogeneous equation. So if you care about uniqueness of solution of this equation, we need to make sure that all these boundary initial problems are formulated in such a way that solutions of homogeneous equation, solutions of the homogeneous equation are empty, because otherwise the solution is not unique. So, but this is some detail which better to study when we talk about some concrete equation, because these things are different between different problems. And there are actually problems that do not make much sense, so-called opposed problems. So, so maybe there should be some comment. So the point is that here T1 and T1 plus T2 solve the same equation. So it's a non-uniqueness of some solutions. Yeah. So do we need to make some break, or shall we just continue? Oh, what do you think? Hmm? Okay. So for how long? For 5 minutes, or? Hmm? Okay. Okay. Let us construct some example that corresponds to the wave equation. So are there any questions about the skip equation? By the way, yes, it can also describe diffusion, because this law that probability, this law that the flow is proportional to a difference of something, like of concentrations or of okay, sorry, I know it is fine. It is delta. So it's not Laplacian, it is literally delta t here. So this law that flow is proportional to difference also works for diffusion, and it can also work in some probability problems, for example, which is more or less the same as diffusion. So if you have some particles jumping between different nodes of this lattice, then this change of probability will be described by probability of jump to neighboring point. So this is why this equation appears in different contexts. So let us now try to study, try to obtain the wave equation. And let us actually draw the same picture as for heat and for Laplace equation. But in this case, this picture will correspond to the actual net. So it is the actual net, which is being pulled in different directions with forces F. And so on. So now each point of this grid corresponds to some body of, maybe better to say it corresponds to some point mass m. And now we have a kind of three-dimensional picture because we have x, y, and we also have a third axis z, in the sense that these masses can move in the perpendicular directions. How to draw it? We can move in the direction. So we have some z of xy, which describes a deviation of this point mass in this perpendicular direction. and parameters that correspond to lengths between different masses are their slopes. Mm. So, so in a little bit more detail, if you look at this picture in a different projection, so if we draw it like this, like z points up, y points towards us, and x points in this direction, then this net or one line in this net will look like this. There will be some points. Located at some z's. So we're in the x lattice, x-axis. There will be some x minus 1, x plus 1, x plus 2, and there will be some z of x minus 1. So, and the slope corresponding to this link equals to a difference of these. Since so it's the same. So for small deviation, the same. Whether we are talking about angles or about slopes, so we have some alpha of x, y, maybe alpha x, and we can write something like a tangent of alpha x equals to approximately equals to alpha x, and it equals to z of x plus 1 y minus z of x y. And the reason why we care about the slope is that if you want to compute z projection of a force acting on this point, we need to multiply the tension of this net, which acts in this direction or in this direction. You should multiply it by the slope. So fz will equal to so for small deviations, it will equal to z of x plus 1 y minus z of x y times f plus another term from the left link. So this will be z of x minus 1 y minus z of xy times f. And so we looked at this picture in one projection, but there will be the same phenomenon in the second projection. Z plus the same for with x exchange with y. And if you now write equation of motion for this point mass, then it gives what? It gives m dz of x y d2 in dt squared t squared equals 2 fz. So the object which is written here is Laplacian, so either lattice Laplacian or it's a continuous limit, but in any case we can write it like this: z tt of well, actually I wasn't writing precise dependence, but it depends on tx and y. So it will equal to f over m Laplacian of z of t, x, and y. And maybe we can write it explicitly. So then it is force applied to each strand in this net. So, of course, there could be some other motions in perpendicular directions, but they will be defined by different things, like elasticity of this strands. So, I'm thinking only about perpendicular motions of this. And of course, okay. Sorry, I wrote this Laplace equation like the limit is already taken, but we can write it as f over m, for example, lattice Laplacian acting on z. Yeah. So this model can equivalently describe some elastic membrane, and we actually see that this operator that appears in the limit in this problem and also in all other problems has rotational symmetry. In a sense, we can rotate this plane and we can also shift it. This limiting operation is more universal, and it is actually a common phenomenon in physics that many theories that have a different microscopic description behave the same when we go to larger distances. So, and here you see kind of first manifestations of this phenomena that this macroscopic equations of motion are the same for well, macroscopic equation of motion of something that consists of atoms do not know about this internal structure. They only take some numbers like some forces applied or densities and that's all. All other details are inessential.
Can you prove that the microscopic and macroscopic are related through the symmetry?
No, I'm saying that even though symmetry at the microscopic level is broken, we have some net. When we go to macroscopic level, when we go to higher distances, then symmetry becomes restored. We can say that it appears at the macroscopic level. And there is also even funnier thing that this equation has some extra symmetry, namely it has Lorentzian symmetry. Because let us put f over m equals to 1. We can do it by choosing some units for time or for distance. So we have an equation ztt equals zxx plus zyy, and there is an exercise to check that so the first exercise is trivial. Check that this equation is rotationally symmetric. And then x y goes to cosine alpha sine alpha minus sine alpha cosine alpha. X y is symmetry. And another exercise is that this transformation t and x goes to hyperbolic cosine of theta, hyperbolic sine of theta, hyperbolic sine of theta, hyperbolic cosine of theta, and t and x is symmetry as well. So it's called Lorentzian symmetry. So this equation that describes some matrix or some membrane or other waves has this extended symmetry. And this this is more or less how people discovered special relativity. So, so the next example I want to consider is about wave equations that appear in some fundamental wave. So these equations were some equations that describe some system constructed by human. But there are some fundamental systems like electromagnetism. So there is electric and magnetic field that are described by Maxwell equations, and I want to show how this Maxwell equations give rise to the same kind of wave equation. Maybe I can write it here. So there is some a simple way to write these equations using four-dimensional notation. So there is a so-called vector potential or four potential, which is denoted by a mu, and is a vector that has four components. The first component is the electrostatic potential, and the next three components are vector potential that is responsible for the magnetic field. So, and starting from this potential, we can construct an antisymmetric 4x4 matrix. Which is given by d nu a nu minus d nu a mu. And if you write this matrix explicitly, then it looks like this. Probably I can miss some signs here. And the idea is the following: that electric field appears here, and here we have bz minus by b no sorry minus bx by, and here it's completed by antisymmetricity minus ex minus ey minus ez. So here, so an exercise is that Maxwell equations for this metric, in terms of this matrix, are written in the following way. Maybe. Maybe I need another blackboard to write this. So, so first I introduce upper and lower derivatives. So when we write lower derivative, then it is a vector of usual derivatives. So it is dt, dx, dy, dz. If we write upper derivative, then it is dt minus dx minus dy minus dz. This is because the indices are raised and lowered by the metric that equals to 1 minus 1 minus 1 minus 1. So there is an exercise to check that Maxwell equations that are written in the Wikipedia or in Maxwell's work can be written in a condensed form like this. So actually, if you talk about Maxwell equation for this field strength F, then we can add another set of equations that come from this formula. The square of this expression. The score looks like this. That d mu f nu rho plus cyclic permutations. Nu d nu f rho nu plus d rho f mu nu equals to 0. So this gives another pair of equations. So this is equivalent to a standard Maxwell equation. So it's one thing. Another thing is that if you talk about this vector potential, a mu, So vector potential the a mu, and a mu shifted by derivative of some function. Plus d mu f are equivalent. It causes some a huge freedom, which is called gauge freedom. And this gauge freedom can be fixed by requiring that d mu of a mu is 0. So why am I writing all this? Because now we can easily write, we can easily obtain the same kind of equation from this Maxwell equation and the definition of f mu nu. So, namely, let us substitute the definition of f mu nu. D mu of d mu a nu minus d nu a mu equals to 0. So now it gives d mu of a nu minus d nu of d mu a mu is 0. So since we applied this extra condition that the mu equals to 0, then this one equals to 0 as well, and so we have a single simple equation: d mu a nu equals to 0. But now, if you look at what this derivatives with upper and lower indices are, you see that what is written here is the following. It's dt squared minus dx squared minus dy squared minus dz squared a nu is 0. So this is a 3 plus 1 wave equation. And since it is fundamentally, because it follows from the fundamental Maxwell equation that do not know anything about such kind of grids or membranes, then people concluded that symmetries of this equation should be symmetries of everything. So first, people discovered a Maxwell equation, and then realized that the symmetry is not what we see in the everyday life, but this Lorentz transformations. So. But you can also see that such equations can appear in some effective theories. And for example, this relativistic wave equation can appear in some condensed matter physics with Mm. This kind of speed of light much smaller than the actual speed of light. Speed of light, and uh, in this sense, this, systems from inside will look more or less like our universe. There's only different that this theory in that case uh, is an effective theory. Mm. So, are there any questions about this? Mm. So. Maybe one remark. So far we saw this wave equation, but if you want to modify our system to get some a Klein-Gordon equation, that it is also easily doable. We can simply add some extra springs here with coefficients k. And if you do this, then the right-hand side of our equation will get an extra term, something like uh, minus k z of xy. Oh, this will be a Klein-Gordon equation. Maybe one more example of of appearance of this wave equation that is slightly different from what we saw before, because in all these cases, original description of a system was linear. In a sense, this equation was linear from the very beginning. But we can consider something that is originally nonlinear, namely Navier-Stokes equation. And
Does that mean we can study it by discretization? We can study it by discretization because you can construct the because it's nonlinear.
Oh, right. We can study it, and when people solve Navier-Stokes equation numerically, they are of course discretizing it. But there is no that nice natural model that would be the actual model that describes some physics. Because here all these models were actually some mechanical or electrical systems. And I don't know whether it is possible to construct some mechanical system that is described by discretized Navier-Stokes equation. We can simply write some discretization, but there is no guarantee that it is something natural. So. Yeah, and actually, there is a little bit similar situation with this Maxwell's equations, but in this case, we can discretize them in some nice way, but maybe in the Euclidean situation when this metric is with coefficients 1, 1, 1, 1. Or maybe, I'm not sure, I never thought about this, but maybe situation when space is discrete and time is continuous, and the signature of this metric is the same, is also fine. Because when people discretize this electromagnetic field, then the picture is like this. Now this field will live on the edges of this lattice, Because you see, it is a vector, so it has some direction, and field strengths will live on the faces of this lattice. Mm, so it's also doable. Uh, mm. And there is this equation. So this differential operator written here means the following: that we take gradient as some differential operator acting on something, multiply by u without acting on this u. So u times gradient equals to ux dx plus uy dy plus uz dz. Actually, I'm not sure that we have enough time to derive something, but let us try. Mm. Maybe for simplicity, we can just ignore this nonlinearity, saying that u is small. Let us write in the second equation dt times rho plus divergence of rho times u is 0. This is mass conservation equation. So, neglect this term because it is quadratic, and if u is small, u is a speed of gas flow. So we neglect this because u is small, and this is quadratic term. And in this equation, we say that rho is some rho 0 rho is some rho 0 plus let us call it sigma. I don't know if it is a good name or not, which is small, and this is big. And here, this pressure is a function of rho. It is defined by some equation of state, and it describes this gas. So, taking into account these assumptions, we can write it like this: so that P of rho is P of rho 0, which is constant, plus sigma P prime of rho. So our equations now look like dt u equals to minus a prime over rho over rho times gradient of sigma. One equation and another equation is dt sigma equals to minus so there are two terms. One when we differentiate rho, but it will be small because the derivative of rho can only contain derivative of sigma. And another term when we differentiate u. So it will be minus sigma times minus rho zero rho zero divergence of u. So there is this system of equations. And if you now want to write a single equation for this deviation of density, we can we can differentiate the second equation one more time and substitute this equation here. So we can write that d at sigma tt equals to minus rho zero divergence of ut and substitute ut from this equation. So it will be p prime of rho zero times divergence of gradient of sigma. So and divergence of gradient is Laplacian. So we get sigma tt equals to p prime of rho zero times Laplacian of sigma. So it's again 3 plus 1 wave equation. And now it describes waves propagating in some gas. Or actually, liquid is also fine. It is much less compressible, but it still has some equation of state, and this derivative of pressure in rho equals to something. So it defines a speed of sound in gas or in liquid. And so.
But then things become crazy and turbulent, right? When you have the higher pressures, you don't have this simplicity anymore.
But I know it's not about pressure, it's about value of U. In a sense, we are studying, first of all, we neglect this term that in the main source of nonlinearity in the Navier-Stokes equation. So describe just small variations. So and this was an illustration of why these linear equations are so important. It's not only because many problems are originally described by them, but also because they appear as linear approximations to some nonlinear equations. And even more, so here we studied some case with zero initial solution. It was perturbation around zero. But people also study perturbations around some non-trivial solutions, and these equations are related to some questions of stabilities of these solutions. So we will not study these equations because they will contain coefficients that depend on coordinates and times, but in principle they can appear in some linear problems. So, for example, people can ask about eigenvalues of some operators, whether they are positive or negative, and answers to this question will correspond to stable or unstable solutions in some nonlinear problem. And in case when we find some instability, for example, of some trivial solution of linear equation, it will be an indication that this linear equation can produce something interesting. For example, some non-trivial pattern like there are, for example, the selection diffusion equations that describe coloring of animals and in general morphogenesis. And there are also some, it's called Turing mechanism. And there are also some nonlinear PDEs. And if I want to study like whether some interesting phenomena appear there, the zeroth step in the study could be the analysis of some linear equation and questions about stability of its solution. So. Okay, so that was all about physics, and next time I will tell about mathematical classification of this equation, these equations, and explain why there is so few of them in so many different problems. Like why everything boils down to just 4 or 5 simple examples. Okay, so thanks for attention.